Hello, everybody. Welcome back to physics. Let me get started here. Swap view. There we go. All right. Um, so today we are virtual. We've got snow and ice and all the yumminess going on outside, along with ridiculously cold weather. So, we're doing this today, and that's okay. We have the technology, we can use it. It's fine. And it's absolutely fine. I hope you guys are staying safe out there. So for us in this class, this is starting exam 2 material. Here our focus is going to be on Newton's laws of motion. So a lot of the work that we would do in a kind of a physics 1 classic mechanics class is going to be based around what we call Newton's laws of motion. There's 4 of them that we're really going to focus on in this point. Now, it's important to point out, just like all other science, science is built off of the work of previous scientists and others. Sir Isaac Newton was no different, a genius in his own right, but Sir Isaac Newton still, his work is based off of and built upon the work of others. For example, Copernicus and Galileo, who worked on, their work was built off of each other, and Johannes Kepler, and there are many others, but these are often kind of credited through history. These are often the main ones that heavily contributed to the work of Sir Isaac Newton. Now, Isaac Newton's, what we credit as Newton's laws of motion. We're going to talk about Newton's first and second law today. We can hint at the third law a little bit. We can hint a little bit at the gravity law also. But we really won't focus on the third or the gravity law until a little bit later. Our goal today is really get a good handle, hopefully, on the first law and kind of build our way up to the second law and allow us to get started with that. So for us in this textbook, that is going to be chapters 5, 6, and part of 13, right? So a little bit out of order there, but it's okay. We're just going to focus on the forces involved in chapter 13. But to start out, our focus is going to be chapter 5. It's really going to be, I don't know, probably 50, 60% of your exam 2 material is going to be chapter 5 material. So we've got a few weeks before exam 2 for us. That's I think it's 3 or 4 weeks, so it'll go fast. We're in a spring semester. Spring semesters right now go pretty fast, but that's where we're headed. Okay, so Newton's laws revolve around forces and how forces cause motion or affect motion or change motion. And there are multiple different kinds of forces. So here's a diagram from your text, from our text that we're working out of, and I've borrowed it. It does a really good job showing that there are different kinds of forces that let's talk about here. But the first thing to mention and really focus on here, I don't know if you can hear the crinkling in the background of I've got a small cat. She's still technically a kitten. She's playing a little bit, so I'll have to ignore her. I apologize. The joys of working remotely. Forces. Forces are vector quantities, right? The direction of these forces are important. You see this guy here with kicking the football. The direction to which he applies a force with his foot onto this ball is very important. That's going to change because now this ball, once he kicks it, becomes a projectile. And now the trajectory of that ball is guided only by the force of gravity once he's kicked it. And that gravity force is going to cause that trajectory to change. But at the instant where he's kicking it, he is applying a massive amount of force to this ball, and the direction of that force. It's important he applies substantial force to get the ball, because if he's trying to kick it away and get it away from the opposing team, he wants to cover a long distance. He wants to push that ball a long distance down the field. So the amount of force he needs to apply is important, but more importantly, the direction. If he applies a ton of force just straight vertical, then this ball is just going to go straight up and then fall straight back down. So the direction of which he applies the force is just as important. So forces are a vector quantity. Both magnitude and direction are both important to cause changes in motion. So what is a force? Think about forces in terms of something that's either pushing or pulling. Pushing or pull, I shouldn't say pulling, pushes or pulls material. Maybe it's enough force to overcome what we're going to talk about, inertia today. It's enough to actually cause motion. Some instances it's not enough to cause motion, but again, that's the whole basis of Newton's first and second laws is how much force is required to cause motion. How do those forces cause the motion to change? And that's going to be based on both the magnitude and direction of these forces. So think of forces as something that's either pushing or pulling on material to cause the motion to change. There are two major categories that we, at physics 1 level, we would suggest there's two major categories of forces. Now, your textbook goes on and does a pretty good job hinting at the idea that really there's kind of 4 fundamental forces. And what we think of and consider a contact force isn't in fact a contact force, but based on kind of electric fields, but that's due to molecular interactions. And as I say, the very bottom point there, at a molecular scale, it's not really contacting, but the good news is we don't have to worry so much about what's going on at the molecular scale yet. And frankly, as an engineer, doesn't specialize in molecular interactions. I'm not the right person to have the conversation about, well, what actually causes contact force? For us, we can keep ourselves just in the normal realm, the macro scale, the large scale, where if I've got 2 objects interacting, looking for my pen here. If I've got 2 objects interacting, I've got my finger here and this pen, I can apply a force to the pen and the pen can apply a force back on me simply by 2 surfaces coming in contact with one another. So when we think about contact forces, these are basically 2 surfaces coming in contact with each other, causing a push or a pull on each other, and therefore possibly changing the motion of each other. And that's contact forces. Now, what we call field forces, I've seen sometimes this is referred to as long-range forces, and I've seen long-range forces being a term used in some texts. I've seen non-contact forces as a perfectly common description we might use for what your text is referring to as field forces, and we're all talking about the same thing. I think we mentioned before, if you're like, Steve, why doesn't everybody just use the same language? Well, welcome to the rest of your life being in science, technology, engineering, or math. Much as we would love everybody to use the same language, not everybody does. So this text calls them field forces, and that's not uncommon. And there's some reasons for that, and I'll let the text kind of talk about that. But field forces for us are going to be any forces that do not require direct contact of 2 objects to be applied. These can be applied over a distance, sometimes very long distances. We're a very long distance from the sun, but the sun is applying gravity to us. So again, in chapter 13, we're going to look at the attraction of 2 different masses. Newton's law of gravitation essentially is telling us that all mass everywhere in the universe applies an amount of gravitational force on all other mass in the universe, and some of it's a substantial amount of force, and some of it's not really a big amount of force. We're close enough to the Earth. The Earth is applying a huge amount of gravitational force on us. We don't think about it because we're used to it. But attraction of charges, that's this middle diagram here. So the attraction of charges. So if I've got a positive charge and I've got a negatively charged particle, there's going to be an attraction between the two. And if it's a massive amount of charge, that can actually cause a spark. That's a whole nother story, but this is basically what causes again, migration of small particles a lot of times on the microscopic scale is by particles being attracted to each other. And kind of very similar to that, but slightly different, is the forces of magnetism. So if I've got a paper clip, for example, I could pick up a paper clip with a magnet using magnetic forces. Anything that's kind of what we call ferric, iron, especially anything that's steel or iron, is going to be attracted to magnets. And there's some other metals that will be attracted to magnetic fields, but iron's kind of anything with some substantial amount of iron in it. Steel has a lot of iron in it, so things like paper clips and whatnot. These are going to be attracted to anything that puts off a magnetic field force. Okay, so those are just kind of quickly, and we really won't in this class worry too much about these two, the magnetism and the attraction of charges. We'll leave those really more for a physics 2 class for the most part. Excuse me. But as I've mentioned, we are going to deal with gravity, both on a large macro scale and then also just kind of looking at out in space gravity and attraction of two different particles with two different masses separated by a distance. That more on that to come. Okay? So right now, let's focus more on kind of forces that we would typically experience, forces that we might encounter, especially in like example problems today moving forward. So let's say we have a physical copy of the physics book. Okay? I know many of you guys are working off of a digital copy, but I happen to have a physical copy of a physics book here that, and you can acquire one. And I encourage you to have a nice physics book laying on a shelf as a nice reference moving forward. This one is no different. I think you could probably buy an older version of this in the physical form, pretty reasonably priced. So let's say I've got a physics book here and I apply with my hand here a certain amount of force, right? Now, I can do it in such a way that the book really doesn't move. It doesn't change. That doesn't mean I'm not applying forces. It's one concept we'll talk about today, is that just because I apply a force doesn't mean that motion is being changed. That's kind of the difference between Newton's first and second law, honestly. But let's say I've got a physics book here and I have a physical book, so I get the satisfaction of just slamming this book out of frustration onto a table surface. Let's look at the forces involved if I were to do such a thing. You have a couple of contact forces here being applied. So highlighted here, kind of grayed out the other forces a little bit. I've got the force, the push that I'm applying with my hand upon this physics book. Just we'll call him force F, just to be generic. And then another contact force we'll encounter very often is what we call the normal force. The normal force. Sometimes we might refer to this as a reaction force. Again, we're going to focus a little more on Newton's third law a little bit later, and that's going to come up multiple times. But Newton's third law, you've probably heard before, this idea that for every action, there's an equal and opposite reaction. The normal force kind of falls into that category. Let's be careful going too much further with it than that. But if we talk just a little bit about this normal force, a little more in depth, that normal force is always perpendicular or normal to the surface that's applying it or causing it. So a normal force is normal to the surface. If I back up here, that normal force, it is not controlled by the direction of this force. It is not controlled by the direction of gravity. It does not have to be vertical. We will see problems where we're on an inclined surface the normal force is by definition normal to or perpendicular to whatever surface is applying it. So in this case, I've got a horizontal flat surface, therefore the normal force is vertical. So very important things there. I'm going to stop share for a moment, and I'm actually going to switch to document camera because this is really important. Just cannot stress this enough. If we expand on this idea of the normal force just a bit more, right, and mostly also I'm now writing some things down to force you to actually maybe take some notes. Go back and add some notes of contact, non-contact forces if you've not already. Hopefully you have. That's important to know. You have contact and non-contact forces. So write that up above here. But if we drill down just a bit on the normal force, does not have to be vertical. It is normal to or perpendicular. Perpendicular. It's normal to the surface. So again, forces are vectors. Something else, hopefully you've written down. If not, write that below here. Forces are vectors. Forces are vectors, meaning the direction of those forces is important, the same as the magnitude. The direction of the normal force is controlled by the surface that provides the normal force. It is perpendicular. It does not have to be vertical. That's a very common mistake I see people, especially in Physics 1, even in some later courses, just assuming that normal force is vertical because it's just out of habit. You will encounter problems here where that's not always the case. All right. I'll switch back to me. I haven't really fixed my hair too much today. I'm not sure I want to switch back to me, but we'll go back to me. Hi. All right. So a little bit of rant there about the normal force. Thanks for bearing through that. Now, can I advance? There we go. All right. So my silly animations here that are kind of working. So again, just to provide some examples here, we mentioned there are contact forces, things where contact between surfaces is required. You have what we call field forces, where contact is not necessarily required. It doesn't mean if there's contact, those field forces don't exist. They exist whether there's surfaces involved or not, or contact involved or not. Gravity always is applied. The Earth is always going to apply gravity to you. You may get far enough away from the Earth that that gravity is insignificant, but it's always there. And the closer you are to the Earth, the more it gets applied. And but if you say you got in an airplane and you're flying around in an airplane, you're not actually touching the Earth, but the Earth is still applying a gravitational force to you. Gravity. And gravity is a force that is similar to a normal force. If I stop share again and go back to video, and I think we mentioned this a little bit later, what we call the weight, which is gravity. Your text likes to use F sub G. Applied toward the center of the Earth. Again, magnitude and direction are important when we talk about forces, forces being a vector. So the direction of gravity is always towards the center of the Earth. Most of the time, we're going to draw that in such a way that that's straight down. Doesn't have to be, but that's going to be the most common thing we're going to do with gravity is apply it straight down. Okay. Now, back to sharing. Okay. So just a simple example is a very simple example of a type of problem that we might encounter where we've got a certain amount of force applied. a certain normal force and a certain gravity force that we're counteracting. Okay, advance. There we go. Now, another force that we are going to encounter is what we call the friction force. All right, the friction force. Similar to the normal force, the friction force is going to be parallel to whatever surface causes it. So let's say that I apply, in the previous slide here, let's say this force is also at an angle. So some of it's vertical, some of it's horizontal. So let's say I push this book just a little bit. If I'm trying to push this book a little bit to your left here, then the friction force would counteract that. Any friction force is going to counteract the tendency of motion, whether motion occurs or not. It's going to counteract the tendency of motion, but it's going to be parallel to the surface. So parallel should read down here, parallel to the surface, but opposite of motion. Where the normal force is perpendicular to the surface, the friction force is always going to be parallel to the surface. And then again, opposing motion. So we'll encounter friction. We're going to talk a lot more about friction in depth in later sections of this chapter, but it's worthwhile to mention right now because I'm going to talk about friction here in just a little bit. Unit of force is the Newton, right? The unit of force is the Newton. We should define that real quickly here. I think I'm going to try to write on the slide. I don't know how well this is going to go. Right. That is not going to go well at all, is it? Okay, that's not bad. Okay, fine. Not sure what's going on there. I'm not sure if it's my mouse or what, but we'll go to the document camera. Okay. Now we're going to talk about units of force in just a little bit here, but it's okay. The Newton. The Newton is the unit of force in the SI system. 1 Newton is equal to, you can say that's 1 Newton. That is a unit based on the name of an individual. Therefore, it gets capitalized. Okay? Therefore, it gets capitalized. And we're going to define what the Newton is a little bit later. Yeah, let's talk about mass and weight in just a little bit before I try to define exactly how that breaks down. Okay. All right, I'm going to go back to an arrow here. Okay. Forces can be combined and subtracted just like any other vector quantity. We've hit on this pretty hard today. Forces are vectors. Magnitudes and directions are important. So just like any other vector quantity, we're going to have to combine them based on those magnitudes and directions. A very common term that you will encounter is what we call the resultant force. A resultant force is just simply what happens when I sum up multiple force vectors. So resultant is actually a term I can apply to just about any vector quantity, but we especially apply it to forces on a regular basis. Okay, so I've got an example here. Let me get it pulled up here. So an example here. Example. We got here page 1 of something. Let's just simply say that I've got some random object here. And let's say that I've got force 1 is equal to, we'll say, 9 newtons. And let's say I've got force 2 here acting. So force 1 we'll say is acting in the negative y direction. We'll say force 2 is acting in the positive x direction. We'll call it 12 newtons. And so 9 newtons down, 12 newtons over. And we want to find the resultant force. I think I'm going to have to find a better pen. So a common way we would write the resultant force, I mean, you could write it as like force sub r, but really what we normally do is we say, well, you know, if this is a vector, we would write a summation sign. The summation sign refers to the resultant force. A summation like this, when we're talking about vectors, a summation of vectors refers to the resultant of those vectors. We're going to add up all of those vectors. So if I'm to find the resultant force, that means I'm trying to find the sum of all forces in the x direction plus the sum of all forces in the y direction. And then if I've got z direction, it would also be the sum of all forces in the z direction. So this is a common thing you'll encounter whenever you're dealing with a vector equation. That means you can break this vector equation down into its components. It's all the directions that are important, in this case, x, y, and z. And then what that means is I can say, well, if I add up the forces in the x direction, right? So if I add up the forces in the x direction, I can add up then the forces in the y direction. I don't have z direction in this particular problem, so I'm not going to have to worry about those. But in the x direction, I have F2. And that's it. Right? And then in the y direction, I have F1. And that's it. That's negative. It's going to be in the negative direction. So F2 or F1 is going to be in the negative y direction. F2 is in the positive x direction. So that's just simply 12 newtons. And Fy is going to be, Fy. Well, the only thing I've got in the y direction is F1. That's going to be minus 9 newtons. It's going down. It's in the negative y direction. So the resultant force then, we can just simply say is equal to, we might say minus, I don't know why I'm starting with the y direction. That doesn't make any sense. We normally start with the x direction. It's technically, I could start with the y direction, but I'm not going to. It's not consistent. I've got in the x direction 12 newtons. That's in the I direction. And I've got minus 9 newtons in the j direction. Now, that's perfectly okay to write it that way. It's also okay to write it, we talked about polar form. Right? So if I've got 12 newtons and I'm going down, and it doesn't matter which way I add them, I can add x and then y, I can add 2 then 1 when I'm trying to find the sum. Doesn't matter which one I add first. And so this is my resultant force, sum of forces. And it's going to be at some angle. We're going to call this angle phi. I'm going to call this angle phi. To find the magnitude of the sum of those forces, that's going to be the square root of 9 squared plus 12 squared, or 12 squared plus 9 squared. If I do that real quick, I believe that's 25, but let's just make sure. 9 squared plus 12 squared equals, and then we take the square root of that. Yes, that's 50. That's not 25. I'm sorry, it's 15. The magnitude of that resultant force is then 15, and those are newtons. Okay, now that's my magnitude. I would like to be able to describe this direction. I've defined this angle here as phi. Right? So if I can, normally I would just say, just write additional stuff. I'm trying to not have to start the second page yet, but I probably should. So I'm going to keep going up here, which is really bad form. I shouldn't do that. So I'm not going to do that. I don't really want to encourage, I don't want to encourage you guys to do that. So let's do this then. So let's find that angle there. So the tangent of this unknown angle phi, again, page 2 of something. The tangent of phi is going to be the opposite of phi is going to be 9 and the adjacent is going to be 12. So this then gives me, well, that gives me a number. And then to find phi really is what I'm after. I would take the inverse tangent of 9/12, which is 3/4 or 0.75. I'll leave it as 9/12. So, all right, so if your calculator's in degrees, 9 divided by 12, inverse tangent, I'm getting 36.9 degrees roughly 37. So phi is 36.9 degrees. Now, normally what I do though is, if I write this in what we call polar form, normally what I want to know is I want to know angle theta. How many degrees measured counterclockwise from the positive x-axis? Well, it's 36.9 degrees negative, essentially clockwise. So if I throw a negative sign on that and I add 360 to it, theta is actually 323 degrees, 323.1 degrees, measured clockwise from the positive x-axis. So if I say the sum of forces, the resultant force, if the problem didn't specify and you just want to leave it in I and J components, that's fine. But we talked about this when we introduced vectors previously. Sometimes you might want to put it in magnitude and direction. And a simple way to write this is what we call polar form, where I write essentially the radius or the magnitude, 15 newtons. And then the directions to write it in standard form is measured counterclockwise from positive x-axis. So you could say that this is 300 and I am having terrible luck with pins today. This is the fourth pin. I've paused and done most of this off camera. I don't know. Anyway, I won't gripe. 323 degrees measured counterclockwise from x. You could report it as a negative 36.9, and I would be fine with it. I don't know if WebAssign is going to take it anything other than 323 degrees, but that gets us to three significant figures. So this would be our resultant force. Again, what is my point here? What is the whole point of this simple, not a real complicated example, is that forces are vectors. You can combine them just like you would any forces. You can combine them just like you would any other vector quantity. How do you report out a vector? You either report it in XY components or magnitude and direction, both of which are correct, and it depends on what the problem has specified, tells you which direction you should apply them. Now, if we continue on then with our discussion of Newton's laws is really what we're after today. So we continue on with the discussion of Newton's laws. The logical place to start is probably Newton's first law. Now, I've alluded to the other laws. I've alluded to Newton's third law and Newton's law of gravity a little bit. But let's focus on Newton's first law first. Newton's first law. How does that go? Well, there's a few things, and your book starts one way, and I'm going to start another way. Let's just do this. Let's say I've got a box, simple object, and if I apply some force to the box, if I apply enough force to the box moves. Simple, right? Forces can cause changes in motion. Newton's first two laws really revolve around trying to describe what that change is and when it occurs and why. Okay. So if I apply enough force to the box will move. But if we know from experience, right, if I have this box here and I apply enough force to get it to move and I leave it alone, eventually it comes to rest. And it's going to come to rest because in most applications, there's going to be some resistance. And almost always that's going to take the form of physics. If I'm just pushing this box along some surface here, once it starts moving, there's going to be friction. And honestly, there's always friction. It's just the friction may be insignificant. And as I get the box moving, then there's going to be an amount of friction. And then if the box comes to rest and there's nothing else trying to get it moving again, the friction essentially becomes negligible. It essentially drops to zero. You see it's dropped off the screen here. But what if, hypothetically, we find ourselves in a situation where there is no friction? Give the box a shove, there's no friction involved. There's a good chance that box is going to move indefinitely, right? It's just going to keep moving down the road. And that means it's going to move kind of at a constant velocity. There's no change in velocity, so there's no change in direction or magnitude of the velocity. If there's no other forces acting on this box, we get it started, leave it alone, and it just keeps going. Now, I've put it here on what's called a parallax, essentially, just this looping GIF image of something going down the road. We can do this with if I shove this box going down an asphalt road, there's going to be friction there. I always like to joke and say, we could go to the physics store and buy a frictionless box and a frictionless road, but that's about the only place we'll find them is some hypothetical physics store, because very few things, if anything, actually exist without friction. But I don't know, maybe we push this box out in space where there's nothing. Essentially, it's a vacuum. There's nothing out there. Like, give this box a shove. If there's nothing else to stop it, it can probably move indefinitely. Today I'm doing these videos and recording. We're remote because there's ice outside on the roads and they're not safe to drive on, most of them. You can probably hear in the background of the video, a snowplow just went down the main highway outside my house, so they're trying to remove the ice. But all that to say, prior to that snowplow that we heard earlier going down the road, there was just a solid sheet of ice out on the road outside the house. So that was going to be essentially very low friction. So I probably could give a box a nice shove going down that road and it probably wouldn't stop. That's the reason we're not driving today. All that to say, there are some situations we can point to that we can basically minimize friction. We can drastically lower its effects. And we could, in theory, be out in space and find a situation where we're out of vacuum, so there is no resistance. There's nothing to resist. So I could probably give this box a shove and it could probably continue to move indefinitely. In all these situations, we're really trying hard to work at this no exterior force or no exterior influence. And that's what Newton's first law revolves around. It's a situation where, in the absence of external forces, an object at rest is going to remain at rest, and an object in motion will continue in motion at a constant velocity, so long as there's no net external force opposing that motion or that rest. And that's Newton's first law. An object in motion stays in motion. An object at rest stays in rest. That's the common way we hear it. Object in motion stays in motion. Object at rest stays at rest. That's true. It's a little narrow. Right? And I've even narrowed this a little bit. You see the ... there. I've cut out something we haven't talked about if you look at the definition from the textbook. But this is Newton's first law. In the absence of a net external force, an object at rest will stay at rest. An object in motion will stay in motion at a constant velocity. Now, let's talk about what kind of resists that motion, that change in motion, resists the effect of a force, if you will. That's what we call inertia. Inertia is the tendency of this natural tendency of an object at rest to stay at rest and an object in motion to stay in motion. And we can so it's both, and we will quantify this with a quantity we call mass, which we're going to talk about mass in a little bit. We talk about weight. Mass provides inertia to an object's linear motion. So if I have something that's massive, lots of mass, it's got a lot of inertia. I really have to give it a good shove to get that box moving down the road, so to speak. That's your inertia. Now, remember, I said that if you look back at how I've phrased Newton's law, first law, I've removed something. Well, that something has to do with what we call an inertial frame of reference. So inertia is one thing. Let's talk about an inertial frame of reference. And we'll move my picture just a little bit here. An inertial frame of reference. So there are situations we can point to where it might appear that this law has been violated, that there's an object at rest might spontaneously appear to us to be moving. That's true if we're not in what we call an inertial frame of reference. An inertial frame of reference, that's we're sitting in a situation that is moving constantly, moving with inertia. Essentially, it's moving. Its motion is not changing. So what is that? Well, the closest we can point to that is an inertial frame of reference is sitting on the surface of the earth. Right? If I'm just sitting on the ground, that's as close as we can come to an inertial frame of reference. Now, that's not technically true because Earth's moving around the sun and the sun's moving around the center of the Milky Way, and that's moving somehow relative to the universe. And there is some change in that motion, all in all those frames. But to us, we're not going to heavily influence the motion of the Earth. So to us, the surface of the Earth is the closest thing we can point to easily and say, well, here's an inertial frame of reference for your reference. Is something moving relative? Is something's motion changing relative to the motion of the surface of the Earth? If it's not, if whatever you're dealing with is either moving at a constant speed relative to the motion of the Earth, or it's at rest relative to the motion of the Earth, that's what we call an inertial frame of reference. Right? So all that to say, again, Newton's laws, all of them, might appear to be violated if I'm observing something that's occurring in a non-inertial frame of reference. It's a silly example, but this is one of the best ones I can come up with. Back when I was younger, there was a TV show on MTV called Jackass, and they did silly things. And this video always comes to mind. Here's a good example of a non-inertial frame of reference. And I know that GIF image there is a bit chaotic. I like his laugh. This is not an inertial frame of reference. So what they're trying to do, they call this roller disco. And so these people are all in the back of a moving van on roller skates. So when something's rolling, there's essentially almost no friction. That's a way we can minimize friction, is to have things rolling. And so if I'm strapped in safely to the back of this moving van, as all these silly people are on roller skates, and as this moving van moves and it is accelerating relative to the surface of the Earth, I might be sitting there with the video camera, as this person here is kind of strapped in, hopefully, and sitting with the video camera, and they're not moving. The person that's recording is not moving. But notice everybody around them all of a sudden starts accelerating. They start moving. But it doesn't appear that anything has caused a force. Nothing's pushed them away from that wall. They just spontaneously start moving away from that wall. It's because the frame of reference, their frame of reference, or the frame of reference of the person recording the video, is changing. The frame of reference is being accelerated. So therefore, the objects around them might appear to move or change their motion relative to the person observing. And that's not actually what's happening. It's that the person doing the observing, the person doing the recording, their motion is changing, and everybody else around them is trying to stay moving at a constant velocity. So this guy is just chuckling because he's changing the frame of reference. He's changing the acceleration. He's accelerating or decelerating the van, and everybody else is trying to move. Their body wants to naturally move in a constant velocity, and they do. So their bodies continue moving while the van around them changes motion. Right. So again, all this to say, just like anything else, you can always pick apart. If you don't understand what you're looking at from a scientific standpoint, it's always easy to disprove. You have people that genuinely believe the earth is flat because they don't understand science or literally just much of anything that they're talking about. This is a perfect example of something like that, where if I'm sitting here watching these people and they all of a sudden spontaneously fly across in front of me and nothing has changed their motion, oh, we violated Newton's first law. No, you didn't. Your motion changed, theirs didn't. And that's the difference, because you're in a non-inertial frame of reference. Hopefully that helps. I know it's a bit silly. Again, I saw this GIF and I saw his chuckle and I'm like, okay, I got to use that. Hopefully that helps a little bit. Okay. So here is the full statement from your textbook of the Newton's first law. Now that we've talked about, and I've tried to hopefully illustrate what inertial frames of reference means. In the absence of external forces and when viewed from an inertial frame of reference, an object at rest remains at rest, and an object in motion remains in motion at a constant velocity. So had we been watching these people in the moving van, let's say the moving van had clear transparent sides and we're sitting outside watching them drive by, and all of a sudden the van stops, but the people inside are just going to keep moving forward. Their motion is not going to change, even though their frame of reference does change. Their motion relative to us sitting outside watching them in, their motion stays the same, because there's nothing stopping their motion from changing until they smack into the front of the moving van. Right? And that's what we saw them flying across, is their motion continued relative to the surface of the earth. Their motion continued even though the van stopped. Their motion continued because there's no external forces on them stopping their motion until they hit the front of the van. Hopefully that helps. Newton's first law. A body at rest stays at rest. A body in motion stays at motion, so long as there's no external forces, no net external forces, and so long as we're talking about an inertial frame of reference. Okay. Excuse me, sorry. Very important here. An object can and often will have multiple forces acting upon it. Those forces might cancel out. Those forces might be, I'm sorry, I just got the message that we're closed again for tomorrow for Thursday for us. We're closed again Thursday due to weather. So I apologize. Anyway, if you're watching this video late and you haven't got the notification, well, sign up for notifications. You should be getting those anyway. And if you're joining us from the internet, you have no idea what I'm talking about. Welcome. Hopefully you learned something about Newton's laws of motion. An object can and will have multiple forces acting upon it. That's okay. Nothing wrong with that. Those forces can add up to be zero, and you have what we call no net force, and then Newton's first law applies. Okay, let's real quick here, let's write that in kind of a mathematical form, if you will. If we were to write Newton's first law in kind of a mathematical form, that would mean that if the resultant force, if the net force sums to zero, if we add up all the forces and we get zero in all directions, then there's no acceleration. So if there's no net force, there's no net acceleration. That's kind of a simple way to write that in mathematical terms. Right, now, so if we continue on from there, Newton's second law. If a body is moving along a surface where there is, in fact, friction, we've already talked about this, the body is going to decelerate. That friction is going to oppose the motion. The friction is going to basically slow the box down. If there's not enough force to overcome that friction, that object's just going to slow down. That's because you have that friction force causing a non-zero net force, slowing down, decreasing the motion. So that tells us something about where we're headed here. So Newton's second law is basically formed on this idea that, and we have just tons and tons of experiments to back this up, that if something is moving along, if we have a constant, if we're able to somehow maintain a constant force applied to a body, we will observe a constant acceleration of that body. And again, we have tons and tons of evidence backing this up. What you find is that the acceleration is going to be directly proportional to the magnitude of that net force. How much force is being applied determines how much it accelerates directly. And it's not even squared or anything. It's a linear direct proportionality. We've just figured this out through tons and tons of experiments over time. What we also find, we talked about inertia, mass being the resistance to that change in motion. We find that the mass, the amount of mass, is inversely proportional to the acceleration. So the more mass, the less the acceleration is for the same amount of force, and vice versa. The more force for the same amount of mass, the more acceleration, but the more mass, the less acceleration. So this is what we find. This is the conclusion that we have reached. I'll write this with you guys. This is very important. So if this is Newton's first law, what I've written on here on the screen, it's small, but because it's right there on the screen with you. Here on the document camera, I've written Newton's first law. We just saw that. Newton's second law. I'm hoping you've written other stuff in your notes, but if you write nothing else, Newton's second law basically says that the net force, the resultant force, the total of all forces added together, causes acceleration in the amount of mass times acceleration. Now, if from what I understand, if we go back to Newton's literal translations of his writings of his first and second law, the second law actually refers to what we call the quality of motion, which later we'll come to call the momentum. And so essentially Newton's second law is saying that if there's a net force, you cause a change in the quality of motion. But this is kind of the more common way we present it today. Now, very commonly, you might see people say, well, F is equal to ma. That's Newton's second law. Well, kind of, yes, technically true. If I apply a force to an object that's otherwise at rest, then that force can cause a mass times acceleration. But really, it is truly if I take the sum of all forces acting on an object, the sum of all forces then are going to cause mass, a total of mass times acceleration. It's going to cause, again, a total acceleration, and it's going to be inversely proportional to that mass. All right, so this is in mathematical form. We've talked about Newton's first and second laws so far. Now, we do need to have a nice discussion about mass and weight. The gravitational force, or what we're going to talk about, we can just call weight here. That your text seems to like to call it F sub g, and that's fine. I will probably, out of habit, call it W for weight. I will do my best to try to be consistent with the text, but if I call it W on occasion, I apologize. That is mass times acceleration of gravity, g, which we said was 9.8 meters per second squared in the negative y direction. So the magnitude of the force is going to be the magnitude of the mass, or the mass, which is scalar quantity, times the magnitude of the acceleration of gravity. Now, that's going to be a force, a single force applied to an object. That's probably not going to be the only force. If we break that down a little bit, we've talked a bit about mass. If we really think about what is mass, mass is what happens if I could add up all of the protons and electrons and neutrons present in an object, then that would tell me about the mass. And I can't realistically do that. We're just now at a point where we can actually observe atoms. We're just now at a point where we have the technology where we can actually observe atoms and maybe stand a chance of trying to count up how many protons, neutrons, and electrons we're talking about. But we're really not there. And it's just not practical because we're talking about trillions and quadrillions in a small object. So that doesn't make any sense. That's not how we actually measure mass, but that's what it represents. Is it just represents the total amount of material present, which breaks all the way down to those base items of protons, neutrons, and electrons. And again, if you look inside those, they're actually made of even smaller components, but that's another discussion for another time that we don't have to get into. So what is weight? Well, weight is the effect of whatever planet or object you're on, standing on, or near. The weight is the effect of the gravitational force of a large body on smaller bodies. So for us, just being small bodies on this massive body of the Earth, our weight is simply the amount of force that the Earth's gravity is pulling down upon us towards the center of the Earth. Weight is a vector. We normally just think about it as this magnitude, as a scalar. Hey, I've got a certain amount of weight. But it's actually, again, it is a vector quantity. It has a direction, as I've mentioned multiple times, that is directed towards the center of the Earth in this case, or whatever the larger body is causing the weight, causing the gravitational force. The direction of the weight vector is always towards the center of mass of the larger of the masses, both masses. And so I am actually imparting a weight on the Earth towards my center of mass. I'm applying a force on the Earth. It's a mutual force, but the Earth is so massive it doesn't care. It doesn't matter to it. It matters to me because I'm small compared to the Earth. So as we mentioned, I can't just go in and count up the number of protons, neutrons, and electrons. The easiest way we've done for a long time, is to measure the weight of an object. That's actually pretty easy. And if we were in class, I would grab some of the old-fashioned scales that they've got where I can compare weight of an object to a weight of another object, or they've got some spring scales. I can pull on it and it causes a dial gauge to go. I'll try to remember to show this to you next time we're in class. But so there are ways, very simple ways I can measure the weight of an object. And what we find is I can just, based on this equation back here, if I know the weight, and gravity is pretty easy to measure, you guys will probably do that in the lab, I'm pretty sure, then the mass becomes the unknown. So if I can measure the weight, then I can use that to calculate the mass. And that's historically how we've done it. So it's kind of confusing that actually mass is the driver here, even though weight's what we really measure. And if you've never really had this conversation about the difference between mass and weight, it's probably confusing. And those of us that work in English units, it's even more confusing. And that's another story we'll get to here towards the end. But a really common thing that we always say is, hey, think about it this way. If I weigh myself on the moon, if you've talked about or listened to anything about the moon landings, we know that the weight on the moon, that the astronauts weigh much less on the moon. And in the International Space Station, they have almost no weight. They do have some weight, but it's much less because they're far enough away from the Earth that the effect of gravity is much less out there. But when you get to the moon is much less massive. So the moon has much lower gravity. Therefore, on the moon, you have much less weight than you would on Earth because the moon has much less mass. However, your mass is the same. You still essentially have the same number of protons, neutrons, and electrons when you get there. So your mass is roughly the same on Earth as it is on the moon. Well, it's not roughly. As long as you don't lose any significant amount of mass, your mass is the same on the moon as it would be on the Earth. Your weight will be different because the gravitational acceleration is different. Units of force. So we talk about units of force here. I'll go to the document camera here. Stop share and switch camera views. Okay. We mentioned earlier units. The Newton is the unit of force. We talked about mass times acceleration as force. The Newton is the amount of force required to, I am really getting upset with pens right now, to accelerate 1 kilogram at a rate of 1 meter per second squared. I'm going to have to use a different color, I'm afraid. I'm going to pause and see if I can find a pen. All right, I got some additional pens. Maybe one of these will work to get us through here. Again, 1 Newton is the amount of force required to accelerate 1 kilogram at a rate of 1 meter per second, or 1 meter per second squared. I've seen this in a few physics textbooks. How much is a Newton? If you're like me, you've grown up here in the States and you think in pounds, you don't think in Newtons. But this one's pretty easy to remember. Approximately the weight of the average apple is about a Newton. I always find that one pretty easy to remember. I've never actually verified that. Maybe we do that in class. Somebody can bring a Newton or bring an apple and we'll put it on a scale and see if it's a Newton. I don't know. I've not verified that, but I've seen that in multiple sources. So it makes sense. That's a Newton. Okay. Now, confusingly, in the English system, again, those of us who've grown up in the States would probably think in pounds. And confusingly, there is a pound force and there's a pound mass. In thermodynamics and fluid mechanics, those of you who want to take these courses with me later, we'll talk pretty in depth about these. A pound force is the amount of force required to accelerate 1 pound mass at a standard Earth gravity of about 32.2 feet per second squared. Outside of engineering textbooks, and especially outside of thermal science textbooks, specific branch within engineering, very rarely will you encounter the pound mass. Your textbook talks about the slug, right? So the slug would be 1 pound force is the amount of force required to accelerate 1 slug of mass at a rate of 1 feet per second squared. This is true. And I don't genuinely know anybody that thinks in slugs. So, but everybody I know can think in pounds. So if something has a weight of 5 pounds, that means it has a mass of 5 pound mass, at least if it has a weight of 5 pounds on Earth. If it's not on Earth, then this becomes really confusing and these are different. But at any rate, good news is we don't have to worry too much about the English units here. Those of you going on to engineering courses later, sorry, we have to train engineers how to use both unit sets. Scientists kind of get by without having to learn too much about the different unit sets, but engineers, unfortunately, we do have to learn about that. So again, good news for you guys. This is probably the last time you'll see what we call the imperial English units much, but those are a thing. They exist. Okay. All right. And the last thing I've got is back to my meeting here. Examples. I think I'm going to stop this video here. I'm going to go ahead and let it export and get it uploaded to YouTube so you guys have got it. And I might try to record an example, although I'm going to see how long this video is. I think that's probably pretty good for today. Get started on the homework. All right. If you're in my class, get started on homework. We talked about this earlier, that it's not enough to know physics. You have to do physics. How do you do physics? Well, the homework's a nice starting place. Get started on the homework. It doesn't matter whether you're in my class or some other class. Get started on your homework. Work on your homework. For us in my class, the homework 2A, I mentioned in some of my notes to you, will take you a substantial amount of time. It's not intended that you do it in one setting. Do it in multiple settings. Spread it out. It is several hours. You should plan on several hours to do that. This is, for us, this is a 4-hour class. That means outside of class, you should plan to try to spend up to 8 hours a week on it. I know that seems silly, but that's how these courses are calibrated. You're not always going to spend that time, and sometimes you need to spend more, but carve out a good over the next few weeks. This is where rubber's really going to start hitting the road for anybody in STEM, especially engineering and especially some of your harder sciences. These assignments are going to start taking more and more time. This is maybe your first dish into that, but spend plenty of time on the homework. Again, you've got until the next exam, which for us right now is the middle of March. So get started on that. Don't let it sneak up on you. If you don't have a whole lot else going on because of the snow and the ice, get started on the homework so it doesn't pile up on you later. All right. I'll be available during regular class time and Zoom, and we'll go from there. Again, I might record you guys an example, but honestly, this is probably plenty for a video today.